Reinforcement learning is hard. That's true. Let's make it less confusing. From classic games like Pac-Man to complex strategy like Warcraft, AI is getting smarter. It even defeated world champions in Go, a game once thought too complex for computers. Even robots are learning to move and dance. Self-driving cars navigate the world, avoiding obstacles. Even on Wall Street, AI is optimizing stock trades in milliseconds. Hello, and welcome to this new video, where we explain in simple terms what is reinforcement learning. Reinforcement learning, or RL, is a type of machine learning where an agent learns by interacting with an environment. It takes actions, gets rewards or penalties, and improves over time. Think of it like leveling up in a game. Imagine playing Mario Kart. Mario is the agent. The track is the environment. The points he earns are rewards, and every crash or mistake is a penalty. His goal? Maximize his score and win the race. That's how reinforcement learning works. Comparing RL to a video game is a great start, but it's missing some key details. To really understand how it works, we need to break it down into its core components. The agent, the environment, the state, the actions, the rewards, the policy, the value functions. The way these components interact with each other forms something called a Markov decision process, MDP, a framework that helps define how an agent makes decisions over time in RL. We won't dive deep into MDP just yet, but just know, it's there. Now let's break down each component one by one. First, we have the agent. That's the AI or system making decisions. Think of it like a robot, a self-driving car, or even an AI playing a video game. Next, we have the environment, the world where the agent operates. It can be a game level, a factory floor, stock market. Environment is not just a passive space. It gives feedback to the agent. Every time the agent takes an action, the environment responds by providing a reward or penalty. This feedback helps the agent learn over time. At any moment, the agent is in a state, basically a snapshot of where it is in the environment. In a game, this could be the main character's position, speed, health, or inventory. Just like in real life, not all places have the same value. Would you rather live in a paradise beach house or next to a landfill? Some states are simply better than others. In Pac-Man, one state has him seconds away from grabbing a power-up. That's great. Another state has him cornered by ghosts. Not so great. Clearly, the first state is more valuable. That's why every state has a value, a number that represents how good or bad it is for the agent to be there. To navigate and interact with the environment, the agent must take actions. It can move left, right, forward, backward, jump or duck, etc. But here's the thing, not all actions are always available. Some actions depend on the state. If the agent is in a narrow passage, it can only move forward or backward. Jumping isn't an option. And just like states, actions also have value. Now, let's look at Pac-Man examples. In this first case, he can go up, right, or down. Left is not available. What would be the best move? In this second case, he can move in all four directions. But are they all equal? In the first case, he should go up and grab the power pellet. While in the second case, the smartest action is to move right, away from the ghost and closer to the power pellet. So, actions aren't just random choices, they're state-dependent. They have different values to help the agent make better decisions. Now, you might be wondering, if states have value and actions have value, which one should the agent use to make decisions? Great question. State values and action values are closely connected. They influence each other. But we won't dive too deep into that just yet. For now, we'll keep things simple. Just know that the agent uses these values to choose the best possible action in any given state. We'll explore the deeper connection in another video. In reinforcement learning, good actions earn rewards and bad actions lead to penalties. As simple as that. Now, what do you think motivates this chimpanzee to memorize numbers and tap them in the right order? It's the treat. The reward encourages it to take on this mental challenge, and that's exactly how RL agents learn too. Rewards drive learning. Whether it's a chimp, a video game AI, or a self-driving car? Remember that question from earlier about state and action values? Well, part of the answer lies in rewards, not just the rewards the agent gets now, but also the ones it might earn in the future. Imagine you're a treasure hunter searching for a hidden chest worth $1 million. That's your reward when you find it. If you're only 10 meters away, your position is almost as valuable as the treasure itself. You're close, and success is within reach. But if you're 10 kilometers away, your position is worth way less. Because so many things could go wrong: dangers, obstacles, or even failing to pinpoint the treasure. This is exactly how rewards work in RL. The further away a reward is, the less valuable it becomes, and this is what influences how state and action values are computed. The exact math behind this? That's for another video. For now, know that rewards shape everything. They help the agent decide which states are valuable and which actions are worth taking. Over time, the agent learns a policy, a strategy for choosing the best actions to maximize rewards. Just like a pro gamer figuring out the best way to win. But wait, if we already know which action has the highest value, do we really need a policy? Great question. In a deterministic environment, it's simple. The best strategy is just to follow the highest value action at all times. For example, if there's an obstacle in a game, the best action is to jump over it. Easy. But not all environments are predictable. Take rock, paper, scissors. There's no single best action. If you always pick rock, your opponent will catch on and play paper every time. You'll lose. The winning strategy? Be unpredictable. Instead of always choosing one move, you mix it up, playing rock, paper, and scissors randomly with equal probability. That's a policy too. So, a policy isn't always about picking the highest value action. In uncertain environments, the best strategy might be to stay unpredictable. Now, how do we actually calculate state and action values? That's where value functions come in. They're mathematical formulas that help the agent estimate how good a state or action really is. They're based on something called the Bellman equation, but don't let this cryptic formula scare you. It might look complicated, but once we break it down, it's actually not that hard to understand. And guess what? That's exactly what we'll do in the next video. Stick around, and we'll decode it together. And that's reinforcement learning in a nutshell. The agent explores, learns from rewards, and improves over time, just like we do. If this video helped you understand RL a little better, don't forget to like, share, and subscribe. It really helps the channel grow. Thanks for watching, and see you in the next one.